This is the 5.1 to 5.2 review. Calculators are not allowed, and it's number 7. So this one says, or tests whether or not you can apply these properties of integrals. So I told you that accumulating from a to b on f gives me 3a plus b. And then based on that, I want to compute the accumulation from a to b on the function f of x plus 1. So there are two ways that you can do this, and I'll do it both ways. The first way is to do it completely analytically. We can rewrite this a to the b f of x plus 1 as the accumulation from a to b of f plus the accumulation from a to b of 1. We know that this is going to be 3a plus b. And we know from our rule of constants that the integral of a constant is simply the constant times the upper limit minus the lower limit. So if I finish that up and combine like terms, I will get a 2a plus a 2b. Now another way that we could do it is we can think graphically. This says I accumulated under f from a to b, and I got an accumulation that was equal to 3a plus b. So now if I take that function and I add 1 to it, it's going to bump the entire picture up 1 unit. So now instead of accumulating from this previous x-axis, I now have some new accumulation here whose height is 1 and whose width is b minus a. So this area would be b minus a. If I add this up, I get my 2a plus 2b, and I get the exact same answer. So let's look at b. Same process. I have g of x. The integral from a to b is 2a minus 4b, and I want to compute this new one. So I'm going to rewrite this new one using properties of integrals. Then I know that this one is the 2a minus 4b, and then I'm going to subtract the 2 times the b minus a using my integrals of constants. If I finish that up, I get a 2a minus a 4b minus a 2b plus a 2a. So I end up with a 4a minus a 6b. If I do it graphically, my original function, accumulating on g from a to b, is 2a minus 4b. Then I'm going to move the entire picture down 2 units. So that means I'm going to lose all of this area that I had. It's not going to be there anymore. So that area has a height of 2 and a width of b minus a. So if I take the original area, which was 2a minus 4b, and I subtract the area that I lost, then I end up at the exact same place. My third and final version of this problem has an integral from a to b. Okay, this one's a little trickier. If I rewrite this, this will be the accumulation from a minus 2 to b minus 2 of g of x plus 2 plus the accumulation from a minus 2 to b minus 2 of a 4. Now this piece is relatively simple. It's the constant times the upper limit minus the bottom limit. But this one is going to be a little trickier. So if you think about when we first developed this whole notation for integrals, we had 2 different things that we could box for our inputs. And we noticed that if we moved a function left or right, as long as we dragged the limits with us, we had the same output for the accumulation. So if we look here at the picture, this one's actually easier to do with the picture. If I start at a and go to b and accumulate some function g, and I get this 3a plus 5b, and then I compare it to this accumulation, we know that if we add things inside functions, they do the opposite of what we think. So this function, g of x plus 2, is actually going to be moved left 2 units. So here's my A minus 2 and my B minus 2, and I'll have the same picture, just moved 2 units to the left. If I accumulate that red, we can see that it's the same as the original accumulation when I was going from A to B on the unmoved function. So this accumulation is actually going to be the same as this accumulation. So now I put those together. I have a 3A plus a 5B plus a 4B minus an 8. Let's see, minus a 4A plus an 8. So the 8's cancel, and I get a 3A minus a 4A is a negative A, and I get a 5B plus a 4B is a 9B. And I'm done.